Hello everyone, we present NeRFCodec. Neural feature compression meets neural radiance fields for memory-efficient scene representation. Neural radiance fields have emerged as a popular scene representation. With its ability to achieve photorealistic rendering, NeRF is beginning to be applied in emerging fields such as autonomous driving simulators, 3D live telepresence, and free viewpoint video. In these applications, the storage and transmission of NeRF will become important issues, which means we need technology for the NeRF compression to achieve high-fidelity 3D multimedia with a compact representation. One line of NeRF compression work focuses on efficient data structure design of feature grids, which involves using parameter-efficient data structures, like factorized grids and hash grids. Despite significantly reducing the number of parameters, these methods still require tens of megabytes. Another line of NeRF compression work focuses on efficient parameter compression techniques, like quantization, entropy coding. However, most works in this field overlook another effective compression method, transform coding, that transforms the original data to another space based on linear or nonlinear mapping. The image compression community demonstrates that the combination of transform coding, quantization, and entropy coding leads to the most competitive compression performance. Recently, there is a work named Masked Wavelet NeRF, which is the first to consider transform coding together with quantization and entropy coding in NeRF compression and achieves promising performance. If we look back at the development of the image compression, transform coding has continually evolved from the early discrete cosine transform to the wavelet transform, and more recently to the nonlinear transform. The continuous evolution has consistently driven improvements in image compression methods. Considering the success of transform coding in NeRF compression, it naturally leads us to think, can we exploit nonlinear transform coding to push the frontiers? Therefore, we introduce NeRFCodec, a NeRF compression framework that integrates nonlinear transform, quantization, and entropy coding for compressing feature planes in plane-based NeRF to achieve memory-efficient scene representation. However, there exist challenges for trivial combination. Existing 2D neural image compression methods obtain such a nonlinear transform by training an encoder-decoder network on millions of images from ImageNet dataset, while it is infeasible to get millions of feature planes of 3D scenes to train such a neural feature codec. So, how do we obtain the nonlinear transform basis? We find that a pre-trained neural image codec can be adapted for compressing NeRF feature planes through partial network modification and fine-tuning for each scene. We conduct a toy experiment to evaluate our idea first. We extract 3 channels of feature planes and input them into a pre-trained neural image codec. We then visualize the reconstructed feature map and analyze its spectrum. We observe that directly using the pre-trained codec leads to a loss of high-frequency energy. However, fine-tuning only the last layer significantly restores the energy. These findings leads to our framework as illustrated here. Our feature encoder E-theta inherits the pre-trained encoder in the neural 2D image codec, except that it replaces the first layer of the pre-trained model with a new encoder head to adapt to the channel dimension of feature planes. Our feature decoder D-Phi consists of the feature decoder backbone D-Phi1 and the feature decoder head D-Phi2. During training, the feature decoder backbone D-Phi1 remains fixed while the parameters of the feature decoder head D-Phi2 are updated. Consequently, the parameters of D-Phi2 must be compressed and transmitted. We also introduce feature compensation module to learn orthogonal factorized vectors to increase high-frequency details on the reconstructed feature planes with a low storage cost. As for quantization and entropy coding, we follow the protocols of these modules in neural image compression. In training, the neural feature codec is jointly optimized with the MLP in plane-based NeRF via rate distortion loss. At test time, latent code, decoder head, MLP in renderer, and residual factorized vectors are transmitted. Our method achieves superior rate distortion performance compared to the baseline methods across mainstream datasets. Here, we provide corresponding qualitative results on NeRF synthetic datasets. From the visualizations, we can clearly see that our method achieves high-quality rendering. Moreover, our method only requires a memory budget of 0.5 megabytes to achieve this high-quality rendering. In conclusion, NeRFCodec is an end-to-end compression framework for plane-based NeRF. We adapt pre-trained neural image codec to scene-specific neural feature codec. Our method achieves high quality with only 0.5 megabytes memory footprint. Thank you for your attention.